Hey everybody, welcome to the Routing and Switching Essentials class. This is the Chapter 1 video. Alright, so when we're talking about networks in general, they send traffic in different ways, or they send data in different ways. So imagine if you had to send a message to somebody in the classroom. How would you do it? You would probably either tap them on the shoulder or say something, but you wouldn't call them on the phone. You probably wouldn't email them, things like that. But if they were at their house, then that would be perfectly acceptable to call them or email them. But if they were in another country, you might not want to call them because of the cost. So you may just want to email them, something like that. So it works the same way in our data networks. Depending on where we're sending and what we're sending to, we'll use different types of hardware. So network infrastructure really is a term that just kind of covers the things behind the wall, the things that people don't see: routers, switches, and firewalls. Most people, when they think about computer networking, just think a bunch of computers all networked together magically, and they don't understand that there's all this equipment in the back. So a switch handles things in the same LAN. Here at Stark State, each classroom is its own network, and when you send data from one PC in the classroom to another PC in the classroom, your data goes into the floor, goes through a wall jack, goes to a switch in a closet somewhere, and then that switch also connects to the other computers, and then so it gets to the other person. So sending something in class goes just from your PC to a switch to the other PC, and that's it. But each classroom is a separate network, and in order to go across different networks, you have to have a router. So if, let's say, you're in C212 and you're going to print in C204 because that's where your next class is, and you want something to be printed and ready when you get there. To print there, then you'd have to hit the switch because you're in your internal network, and then the switch would forward it to a router that would route between the different network. Alright, and then let's say you were going to print something at home or do something on the web. Now you have to go across a firewall because you're going across a different WAN. And then we covered LAN and WAN basics in intro networking. But if you have any questions about that, let me know. So the main point is it depends on where you're sending data. If it's in the same LAN, it just goes across a switch. If it's across different LANs, it's a router. And if it's going across the WAN or the internet, you're going to go across a firewall. Alright, give me 3 ways that you would address a piece of information. So in other words, if your PC is going to send something to me, what are 3 addresses that would be on that piece of information? Alright, so think about how would I distinguish that piece of information came from your PC? What would be in the data that would say it was from your PC? How would my PC know where to send it back to? Alright, obviously your PC has an IP address. Your PC also has a MAC address. Now a MAC address is hard-coded onto your NIC card, and it's something that switches use, where the IP address is something that you either create manually or you get from DHCP, and then that's what's used for routing. And then a port number would also be on that packet, depending on what you're sending it to. Like if you're sending me a file on FTP, it would be on port 21. If you're doing something on Telnet, it would be on port 23. Firewalls typically look at port numbers. And obviously your PC has a name. Here at Stark State, they're all like by the room number. So my PC at the instructor desk is C212 PC00. So your PC has a lot of different addressings that go on each piece of information as it's being sent. And that addressing information is read by different pieces of hardware. One piece of hardware may need to read the IP address, one piece of hardware may need to read the MAC address. So it's the same thing with sending a letter in the mail. When I mail a letter, what's the first thing the post office looks at when my letter hits the sorter? When the sorter gets it, he probably looks at the country. Then he probably looks at the state to make sure it doesn't have to go routed anywhere else. But if I'm sending it to, let's say, my neighbor just down the street, then it's in the same city. Well, when the letter carrier gets the mail to deliver, he doesn't look at the state. He doesn't look at the country because he knows any mail that he gets is going to be for his area. So he's looking at street number and street address. Something like 1313 Mockingbird Lane. So it's the same way in networking. Different pieces of information are on each piece of data, and then as that piece of data travels through the network, different hardware reads different portions of that. Just like when you send a letter, different pieces are read at different stages. All right, so again, same thing. Remember, don't forget, a switch looks at the MAC address. So when you send data here in the classroom to somebody else in the classroom, the only thing that's being read is the MAC address. All the other information really is irrelevant on the packet. But because your PC doesn't know where the destination is, he has to put all that information on there. All right, a router looks at the IP address. A firewall typically looks at port numbers. All right, so some terms from your book to remember. A converged network. Converged network just means we do voice and data on the same lines. Years ago we separated that stuff. Like at the foundation where I used to work, they had a video network for the radiology equipment, the MRI, the CT cameras, things like that. And then they had a data network, and then they had a phone network. So there were 3 different networks inside the building. Obviously, through the years we've kind of mixed those all together, so now we get phone, voice, video, and data all on the same network. So that's a converged network. All right, resiliency. How resilient is your network to disaster? What happens if you lose a hard drive? What happens if you lose a server? What happens if a switch goes down? What happens if a link goes down? So it's just resiliency is just how resilient is your network to issues. All right, and then ingress and egress. Your book talks about ingress and egress as in and out, and I've always remembered it as ingress is in, and then egress, the E is for exit. So ingress, the ingress port on a switch is the port that data is coming in, and the egress port is the port that data goes out. All right, scalability. Scalability is your ability for your network to grow without having to redesign or add a bunch of equipment. One example, like when we bought our phone system, we had about 200 users, but we bought ports on the phone system for 250, and that way we could add another 50 users without having to add a whole bunch of new hardware into the phone system. All right, modularity. Cisco kind of pushes this modular approach now, where PC is connected into a switch, and then that switch connects to a central thing, and that way, if something happens to the line between the switch and the central connection or a PC, you're only taking down small parts, and you can build these modules together. All right, then flexibility. Again, how flexible is your network to change? That's kind of self-explanatory. All right, so Cisco's design model has 3 layers: core, distribution, and access. Now, in all reality, what you're typically going to see is what they call a collapsed core. There's only 2 layers, and in that we eliminate the distribution layer. But it looks like this. You've got your core layer, which is your backbone. This is where you'd have your biggest layer 3 switches, your routers, your firewalls, everything would be connected. Your servers would be connected to the core. Then you have a distribution layer. And again, these can be layer 3 switches, and we'll talk about the difference between layer 2 and layer 3 switches eventually in this class. And then that goes down to the access layer, and the access layer would be your lowest end switches, and they would provide access for the users, the PCs. Now, Cisco pushes that model because obviously it makes them sell more equipment, but in reality this is what you see. You see a collapsed core. You see a core network and then an access, and we get rid of the distribution layer. The only time you need I guess the big 3 layers is is when you're dealing with very large networks, multinational companies, things like that. But your average everyday company, 500 employees or less, does not need the 3-layer model. The collapsed core model will work fine. All right, so switches. Switches come in 3 different styles or form factors. The first one is fixed configuration. Now the switches in the back of the room are fixed configuration, meaning you can't add any functionality to them. You can't add a module to make them a file server or something like that. You can't add extra ports to them. If you buy a 24-port fixed configuration switch, you're stuck with 24 ports unless you buy a new switch. All right, next one is the stackable. These were popular a long time ago, but not so much anymore. Basically, in the back, they have special ports, and then you buy special cables, and these cables are very expensive, hundreds of dollars a piece. And basically, using these cables, you kind of daisy chain the switches, and then the ports here are connected to a special board which allows the switches to act as one. So instead of having 4 24-port switches, you actually have one giant, 24 times 4 switch. The idea behind this is if you just take 4 fixed configuration switches and you plug switch 1 into switch 2 and switch 2 into switch 3 and switch 3 into switch 4, and a piece of data has to go from switch 1 to switch 4 and out, without you doing stackable, it comes into 1 makes a decision, sends it to 2 makes a decision, sends it to 3 makes a decision, sends it to 4 makes a decision and sends it out to the host. So obviously that's 4 decisions, where with a stackable configuration like this, when a piece of information comes in, it hits this key, this motherboard part, and it says, oh, that's for 4, so it automatically goes through the chain and then goes out 4. So there's only one decision made, so it acts as one switch. Again, this was popular years ago, not so much anymore, but you may still see these in wiring closets. Today, this is really what we use when we have to have bigger switches. And this is a modular configuration. So basically, the very first time you buy this, you have to buy this cabinet, then you have to buy the 2 power supplies. Obviously, you want to have some redundancy in your power supplies. And then you got to buy the first blade or shelf that you put in here. And then after that, every time you need to add ports, you just, go buy another blade and you pop it in. So this one's got 1, 2, 3, 4 empty. But you can pop in a bunch of different things. These are 48 port switches. These are probably router pieces. But you can kind of build it, and it's modular, so you can stack it any way you want to. Again, the upfront cost is very high, but then after that, it kind of grows, and then it's cheaper to add the blades than it is to buy a whole new router or switch. Alright, so when you go into buying a switch, there's a couple things you have to look at. First one is cost. How much money do you have? Sadly, the IT budget is not, unending. We always have a budget that we have to follow. Second one is port density. How many ports are you going to want to buy? If you got 20 people that need access, do you buy a 24-port switch so you can only add 4 more people before you got to go buy the new piece of hardware? Or do you buy the 48-port switch now so that you can add a whole bunch of people and don't have to do something? So you got to make those decisions. Manageability. Do you want a managed switch so that you can get in there and hit the web interface, turn features on and off, that kind of thing? Or do you just want a dumb switch? You just want to switch this in a small closet with only 3 or 4 users, and you're not going to do any VLANs or anything like that on there. All right, and then PoE. Do you want power over Ethernet? If you're doing voice over IP phones or you're doing wireless, you may want some PoE ports because getting an electrician to wire extra electrical outlets in your ceiling for the wireless access or a different desk for the phones can get expensive. All right, and then port speed. What kind of speed do you want to get in your ports? Do you want 100 speed ports? Do you want 1,000 speed ports? And then when you're looking at the port speed, you have to think about your backbone and what's your total connection speed. So let me give an example. Alright, so here you got a PC. Yeah, I know, don't laugh at my drawing. Here you got a PC, and he connects to a switch. This is an access switch. And then he has a backbone line that goes to the big switch that goes to all the different servers here. Now, if this guy is, 100 megabits, kind of work on my writing skills, and he goes here, if this is a 24-port switch and 24 people are on there, then you got 24 times 100. So you've got 2,400 bits trying to go across from this switch into where all your services are. Well, if this is a Cat6 cable which is 1,000 megabits, then you can't give all 24 people their full speed. So now imagine if these were all 1,000 speed because you did, I want to do Cat6 to the desktop. Well, now you got 26,000 megabits coming into this switch, and then he's got to send them to the main server where email and the files and the electronic medical records and the scheduling program where all that stuff is. So now you've got one Cat6 cable, but you've got 26,000 megs of data trying to go across there. So, and that's why in most businesses you still typically see only 100 megabits to the desktop, because then they'll take 2 or 3 of these Cat6 cables and they'll bind them together. So now that's 3,000, which would handle all 24 people at 100 speed. So when you're picking out your port speed, you got to kind of think about that stuff. You have to think about your data and the path all the way through the network. If everybody gets on at the same time and everybody's working, where would I be at? Where would my slow point be? All right, again, the last one is throughput, and again, that's your bandwidth is typically measured in throughput, which is how much speed can the switch actually process. Just because you buy a 24-port switch that's 100 megabits per second does not mean that that switch can process 24,000 megabits per second or 2400 megabits per second. And that's the difference. That's why you can get onto cdw.com. And if you look at the different switches, you'll find a 24-port switch for a couple $100. Then you'll find another 20-port switch for $2,000. And there's no difference other than they both have 24 ports. They're both 100 speed. But the difference is one can handle full speed of all 24 ports at the same time. The other one can't. The other one, the 200 one, may only be able to handle 1,000 ports. 1,000 megabits per second. So maybe only 10 ports can go at full speed, and then after once the 11th port gets on, everybody starts to get throttled down. Where on the $2,000 switch, everybody, all 24 users can operate at full speed. So a lot of decisions to be made in switches. All right. So what does a switch do? A switch learns the MAC address from the source and forwards it based on the destination address. So in other words, when you first turn on a switch, it's got a MAC address table that it learns. And obviously at first the table is empty. So when PC1 is going to send something to PC2, when PC1 first sends something to the switch then records the source MAC address and puts that in the table. And then he doesn't know where the destination is because he's never talked to PC2 yet. So what he does is he then broadcasts that out to all the other ports. So PC1 is connected to port 1, and when he sends something to PC2, it comes into the switch. The switch doesn't know where to go. So the switch then forwards that information out ports 2 through 24. So all other ports except for the one that it came in on. And then obviously it finally gets to PC2. Well, when PC2 gets the information, then when he sends his reply back, that's when the switch learns the address of PC2. So your switches learn the MAC address from the source field. Alright, so switches obviously learn this, from the source field, which is learned from the ingress port. We learn from the ingress port, we forward out through the egress port. And then those addresses, as we learn those, are stored in the MAC address table. Now your book also calls this the CAM, the Content Addressable Memory. So when you turn a switch on, it tries to learn the MAC addresses of the ports. And that way, the first time PC1 talks to PC2, it has to broadcast it out because it doesn't know where PC2 is. But once PC2 replies, then all the conversation between PC1 and PC2 is just forwarded in port 1 and out port 2. And the other ports are all free, and there's no more broadcast. So that's the big advantage of a switch. When you have a hub, if something comes into port 1, the hub automatically pushes it out to all other ports. It never learns anything. A hub is like a dumb appliance. When something comes in, it gets forwarded out all other ports. With a switch, when something comes in, it gets forwarded out the port that it's destined for, assuming that the switch knows what port that is. Alright, so your switches are dealing with frames. So frames come into the switch through the ingress port. The destination MAC address of the frame is compared to the listing in the CAM for a match, or the MAC address table. And if there's a match, it's forwarded out the egress port. If there is no match, it's forwarded out all ports except for the ingress port. And that's very important because the more broadcasts you have, the more ports are getting spammed with traffic that they don't need. And remember, if you're dealing with half duplex, that's an issue because then your PC waits for the line to be clear. If you remember your carrier sends multiple access with collision detection, before your PC will send, he waits for the line to be clear. But if you're constantly getting broadcast, then the line's not clear and your PC won't send. So just make sure you understand that we learn the MAC address from the ingress port, where basically we get the source MAC address from the ingress port as the packet comes in. Then we look at the destination address and we determine where it's going to go. If we have a listing of that address, then we only send it out that one port. If we don't have a listing, we send it out all other ports. So if something comes in from port 1, we'll forward it out ports 2 through 24. All right, switches. Switches use hardware to make these decisions, and they're called ASICs, Application-Specific Integrated Circuits. So depending on which ASIC or how many you have, that affects the cost of the switch. So like we talked about the $200 versus the $2,000, the $200 may just have one cheap ASIC, where the $2,000 may have 4 top-of-the-line ASICs. All right, and then for forwarding methods, there are 2 methods out there, and really everybody nowadays is using store and forward. In the early days, they used cut through. So basically, they were trying to make data move as fast as possible. So with cut through, what happens is, as the packet's coming into the switch, the header information is read before the data. As that header got into the switch first, the switch would look at the destination address and start making the decision. So the data portion may not even fully be inside, so the entire frame isn't inside the switch yet, and the switch would be making a decision and forwarding the packet. Now the problem with that is, if the packet came in and it was damaged, it was still forwarded anyway. So that was called cut through. So now what most of the switches do, and again this is Cisco's default method, is store and forward. And with store and forward, what happens is the entire frame comes into the switch and is stored, then it's read, and then it's forwarded. So we receive the entire frame, check it for integrity, then we make the forwarding decision. And this saves us, because if the integrity of the frame has been damaged, or the frame is damaged in any way, we just the frame is dropped and we don't have to make the forwarding decision. We can move the next one up faster. All right, so store and forward again has error checking. At the back of the frame, there's an FCS or a CSC, a cycle redundancy check, or a CRC, a cycle redundancy check, or a frame check sequence. Basically, all it is they take, let's say, the number of ones in binary of the entire packet, and then that's what the number will be. So let's say the entire packet has 101 ones. So the FCS will be 101. So when the switch receives it, he'll add up the ones, and if they don't add up to whatever the FCS says, then it knows that that packet got damaged or modified in transit, and it'll drop the packet. It also allows us to use buffering. In other words, we can have different speed ports on the switch. We can have a piece of data come into a 100 megabit port, receive the entire frame, and then send it out the 1 gigabit port. With cut-through method, you can't do that. All ports need to be the same speed. And again, store and forward is Cisco's primary switching method. Cut-through, we already talked about it. It's rapid, but obviously there's issues, and they could fragment packets. All right, collisions and broadcasts. Each port on a switch is its own collision domain. So if you have a 24-port switch, you have 24 collision domains. And if you remember from your intro networking class, a collision is when your data is moving out to your switch at the same time the switch is sending to you, and your data collides. Now obviously that's very bad. So if there are broadcasts, you can have a lot of collisions. Now, one thing to make note here, with full duplex networks, you do not have collisions. So we talk about collisions a lot, but really this is it's old legacy stuff. When they first started teaching networking, everything was half duplex. So your send and receive were using the same line, so you couldn't send if you were receiving. And obviously each collision was an issue. You couldn't send anymore. For the last, 5 to 10 years, so let's say 5. You've had full duplex, so we don't really have collisions anymore. But because there are a lot of older networks out there, your book still talks about this, and it's still a topic on exams and on certification tests. So be ready. All right, so each switch is its own broadcast domain, meaning a 24-port switch is still one broadcast domain. So in other words, if my PC is on a switch, if something is sent directly to me on my port, I'll have a collision. But that doesn't necessarily mean anybody else has a collision. So if there's 24 ports, you have 24 collision domains, meaning if a broadcast came through at the same time that all 24 of us were trying to send data, there would be 24 collisions. Now, there's only one broadcast domain, because when a broadcast comes into a switch, the switch sends it out all ports. So the same broadcast gets sent out to all ports. So there's nothing to stop or limit a broadcast on a switch by default. Now later on we'll talk about VLANs and a way to use those to stop broadcasts from propagating across switches, because in big networks you have a 500 port switch. But make sure you're good with, if you got 24 port switch, it's 24 collision domains. If you have a 24 port switch, you only have one broadcast domain. So switches don't break up broadcasts, but they do break up collisions. All right, let's see how much you learned. So pull out a piece of paper, and I'm going to ask you a couple questions and see if you can answer these. Actually, to see if you can answer these off the top of your head. So first question. What port is used when a switch learns information to populate the CAM? What port is used when a switch learns information to populate the CAM? All right, hopefully you said ingress. So the ingress port is used, or the source port. So either way, that answer works. All right, question 2. What is Cisco's primary switching method? What is Cisco's primary switching method? We only talked about 2. All right, hopefully you said store and forward. All right, a collapsed core network usually eliminates which of the 3 layers in the Cisco design model? So collapsed core network. So remember, in the regular design, there are 3 layers: core, distribution, and access. Which one of those is eliminated in a collapsed core design? All right, hopefully you said distribution layer. All right, the ability of a network to grow without adding a lot of new hardware or having to be redesigned. What do we call that? All right, hopefully you said scalability. So scalability is the ability for a network to grow without adding a lot of new hardware or having to be redesigned. And finally, a 48 port switch contains how many collision domains? So how many collision domains in a 48 port switch? Hopefully you said 48. Remember, your switch does not break up collisions. A switch only, it breaks up collisions. Does not break up broadcasts. Woo, it's been a long day. All right, so you don't have to worry about that. So homework. If you have not read Chapter 1, make sure you read Chapter 1. Log into the Cisco Academy site this week to make sure you can log in. Remember, it's very important this first week that you get logged into the Academy site so that you can start doing your assignments. Take the Chapter 1 assessment on the Academy site. Remember, every week there's an assessment that you have to do on the Academy website. All right, also do Quiz 1 and Angel before Sunday at 11 when it locks out. And then before next class, read Chapter 2. And then we'll be doing a lab for Chapter 2. All right, so again, if you have any questions about anything, bring them up. Email me or bring them to class during lab day. So remember, as a Web 2 class, you're going to get the lecture here at home on these videos. If you've got questions when you read the book or watch the video, you've got to bring them to class. Because again, I don't know, that you have a question unless you bring it up. So don't pay $400 for the class and then not ask questions. All right, so see you guys in class.